Okay, so what I have here set up right now is a variable auto transformer here. Basically, this will just take normal AC power, 120 volt power coming out of your wall socket, and basically we can do an auto of, we can vary the amount of voltage that comes out by simply just turning this dial here. And there are two different inputs, whether or not we're using the 120, which is at the down position, and then the 140, which other countries use. Maybe it's 110 or something, but typically we don't use the 140, we're just using the 120. And the way that this dial actually works is as a percentage of the total voltage coming in, so it goes from 0 to 100%. So we can go from 0 volts all the way up to our 120 volts if we want to, but since that actually provides quite a bit of current that flows through here, we won't go much past 5%. So hopefully we don't see any smoking or sparking, or hopefully no death involved either. But here I have the multimeter. I have it set to the alternating current voltage setting, as opposed to the direct current. So if you remember when you were working with your multimeters, the direct current basically had the symbol of a solid line with the dashed line underneath it. Alternating current basically has this tilde or squiggly line indicating that it is alternating in time. I've just set it to a low voltage setting, so around 2 volts. This will give the RMS value of the voltage that comes out, and not the peak voltage that we can effectively see. And I have it hooked up via, in this manner, coming out of basically a standard socket port in the front of the variable auto transformer. So if I turn this on, it's at 0%. However, we're getting a small amount of voltage coming out. If I just kind of push it down as far as I can go, it will try and go to 0 as best as it can. So if I increase this, basically we can get a few volts out from that. And so this would be around, well, let's see where I'm at, about 1%, 2%. This might be a little off. If I need to, I can go up to the next level to about over 2 volts. So if I go, say, about 4% here, we get about 5.3, 4% of 120. Yeah, that sounds about right, about 4.8 to 5 volts, but this isn't quite that accurate, so we don't really care too much about that. But that's basically how this works, and we'll read it in this particular manner. Basically, the multimeter knows how to read the varying alternating current for us in that manner, and we'll display the RMS value. Alright, so that's basically a demonstration of that. What we're really wanting to look at is not the auto transformer itself, but what can be a consequence of using an alternating current, and the function of why we use an alternating current, say, for power transmission. And one wonderful thing that we can do with power transmission is, we don't have this off. I should be more careful about that. But no death, we're good. Everything's good. Alright, so I'm hooked up to my auto transform to the small coil, and then here I will hook up the multimeter to the big coil. Turn this on, and if I turn this on, right, and if I increase the voltage, we should start to see something in just a little bit. not a whole lot. Okay, so actually this is a step down. I'm actually incorrect on what I was saying before, in which just that, like that. Making sure that I'm not getting too hot because I can already smell the wires heating up. So we got up to about around say 5%. We got about 0.11 RMS voltage out of that. So let's check to see what happens when we do the other side. Alright, because I was smelling that it was getting kind of hot. These probably got a bit warm too, so let's be careful of that. Make sure that I'm not burning myself. Okay, so let's just switch it like this. Alright. Oops, I forgot to turn that off again. Silly me. Just make sure anytime you're working with high current stuff that you're safe about that. Crazy Tim probably should care more. But it's a little danger in the pursuit of science. Fun. Okay. Alright. We have it hooked up in the opposite way, where we have the power source that's going to transform its power into hopefully a larger voltage that we'll see out in our multimeter here. And I'll go up to about 5% again of 120. So we'll see what we get out of this one here. Not a whole lot. Turned it off, forgot to turn it back on. That'll work. Alrighty then. Let's turn this back to this so that we have about the same. Okay, about 5%. It's actually a little less. Yeah, so a little less. So this is actually stepped down. So we found that with a large number of coils to a small number of coils, that's a step down, at least in this configuration here. The difference was that we had about 0.07, 0.08 volts when we had it in this configuration. When we had it in the opposite configuration, we had about 0.11. Alright, so this is roughly, if you want to do a little bit of math for yourself, this is roughly a 7 coils to every 7 turns to every 2 turns on this particular transform. And whether or not it operates under the same circumstances as the standard transformers that you're probably learning about now is a whole nother thing. Whether or not that will work out to give you the correct amount of voltage out based on what we conducted here for this particular demonstration. So that's something to look at as well. And a particular function of using not only magnetism, but also producing a electromagnet, and putting these electromagnets together in some way via some sort of connecting core, and that you can create a transformer that can be used as a way of essentially transforming the amount of voltage and therefore the amount of power that's transmitted, say from your power source, to whatever is needing that power, say your homes, business, school, that sort of thing. So these actually have a real application just beyond a little bit of a novelty that was kind of demonstrated when I was just kind of pulling up either some, some paper clips or some iron filings or something like that, they do actually provide us with some sort of function beyond that. And you can certainly look that up even more beyond that. I'm not particularly sure what this bolt is made of. I thought it was made of sort of a nickel. Maybe it's also steel as well, but it didn't seem to have that effect. Like with this iron nail here, where it seemed to have kept a little bit of its magnetism. But then again, I was also running an alternating current, which would then mean that the direction of the current itself was changing, and therefore the magnetic field that's produced inside here would also change. So the reason why this works is because a magnetic field is changing, and therefore the flux is changing inside here. And so this produces that current or that voltage that we see in our multimeter. We can only get an induced current if we have a change in flux. It's not simply good enough to have a magnetic field being produced. This magnetic field either has to change in time. It doesn't have to necessarily be oscillatory, but in this case it is, and it's periodic in a sort of sinusoid manner. But you can also have other things like the size of the coiling itself can change in time as well, or just change in general. This will also essentially change the cross-sectional area in which the magnetic field is flowing through, which produces our flux. So our flux is essentially B times A. And then there's also a factor of N in there with the number of coils that are inside the electromagnet itself. It could either be a solenoid like this, or could it just be a simple coil of wires that could look something to this effect, where it may look more bundled together and a little bit neater than this, but effectively that's the difference between a solenoid and a coil of n number of turns, is that this is more structured in that it has sort of a length dimension, whereas a bundle of wires basically is just a bundle of wires just sitting on your tabletop to that extent. Alright, so you need to change, again, just to reiterate how the transformer works, you need either the magnetic field to change that you're producing, the area of the magnet itself that's producing the magnetic field, or the number of turns. So any one of those three numbers has to change. Generally, changing the magnetic field is the easiest, because generally this is directly proportional to the current that's being supplied. So if you can change the current easily, that makes your life much easier in terms of producing, say, a transformer or an electromotor or something to that effect, depending on what exactly you're trying to produce by inducing a current in a separate coil itself. All right, so basically this changing magnetic field, if we're going with that, in this case it is the case that the magnetic field is changing in time. This produces essentially a reaction by the other coil to produce itself a equal and opposite magnetic field inside. All right, so you can kind of think of it as a reaction to the magnetic field that's being changed in time by this primary coil here that I'm holding on to in my fingers, versus the secondary coil here, up here. All right, so the secondary coil will produce essentially a magnetic field in proportion to which you get to the original flux that you originally had. So the changing flux is what really makes that. And if what it wants to do is it wants to try and retain the original flux it had when it started. So if it had zero magnetic field inside here, it's going to want to try and produce a magnetic field that will counteract the changing magnetic field such that it comes back to zero itself, if that makes any sense. So say this is going to a max B field of, say, 1 Tesla in this direction. This is going to produce a max B field that will counteract it at 1 Tesla in the opposite direction. And so what will happen is that this will produce a current inside in order for that magnetic field to exist in some sense. So the magnetic field has to exist coming from this current here, produced in this wire. And so this wire will then produce a current, which can be registered as a voltage if you know the conversion accurately enough for the resistance of all that stuff, the intermediate resistance. Okay, so essentially that's what's happening, is that this is basically trying to resist the change that's happening from the object that's causing the change itself. So that's kind of a way to think about it in some sense, is that this will just kind of do the opposite of what this is trying to do. Think of it as the obstinate child and sort of the authoritative parent, telling the obstinate child to, do their chores, and they're just going to resist backwards against that. So that's a way to think about how that's sort of functioning inside this transformer. So, and this is also the basis on which electromotors also work too. So to produce an electrical current, say through wind power or hydroelectric power, basically you have a magnet that's being rotated by some sort of fluid, either by air in the case of a windmill, or a hydroelectric dam. You have flowing water that spin turbines that have magnets attached to them, and those magnets, while they're spinning, will change the flux that's appearing inside whatever surrounding coil of wires that you have to produce an induced current. Okay, so that's essentially the basis on which a lot of our power is generated, for the most part. Even in traditional fossil fuel power plants, they generally run in the same manner, except instead of using water in its liquid form like a hydroelectric dam, we use steam. So basically we're just burning coal and oil, or in some instances garbage, to basically produce boiling water that will eventually turn turbines that will then eventually turn those magnets to essentially induce a current in a nice coil like that. So almost all of our power is based on a simple change in flux mechanism, such that we transform changing magnetic fields into electrical currents that will then power what we call modern day society. So I think that's about all I have to say so far about what's going on in this lab. If you have any questions, don't hesitate to ask, as usual. If you have any comments or questions or anything like that beyond that, certainly tell me such. I'm more than happy to take criticism on anything that I might have done errantly, or I can always improve on, so don't hesitate to tell me otherwise. So hopefully you're enjoying your time away from school for the most part. I would like to get together and meet over Blackboard Collaborate, just to see how progress is going for you guys, in case you have any immediate questions for me, or you need some resolution to something that's not working out. We can always talk about it during that time and get the adequate help for that and see how things are going. So if you enjoyed this, hopefully you did. Science, I love science, and I hope you guys do too. And I hope I didn't bore you to tears with these demonstrations and stuff. So again, just kind of reiterate what we're trying to do here. Hopefully you guys can make an adequate battery from mundane things that you can find around your house, and hopefully produce an electromagnet that you can then pick up some iron-based things like staples or paper clips, and then you can kind of vary sort of either how you're constructing the battery, see if you get